In this video, we are going to talk about semi-infinite conduction and share a lab that we created that could help students do their very own semi-infinite conduction modeling with food. So first of all, what is semi-infinite conduction? Semi-infinite heat conduction is a thermal model that can approximate a temperature profile of an object. For short periods of time, most bodies can be modeled as semi-infinite solids since heat does not have sufficient time to penetrate deep into the body. This has many applications, such as the rapid quenching of metal that, when used for swords, can make the outer layer hard and sharp while the inner layer ductile because of the rapid cooling of the outer areas of the sword relative to the inside. Semi-infinite modeling can also be used for things like internal combustion engines and even temperature modeling of Earth. Here is a fun graphic of semi-infinite heat conduction temperature profiles at different boundary conditions. The left image shows a constant surface temp, the middle image shows a constant heat flux, and the right image shows a constant surface convection. There's an interesting analogy that we found describing what a semi-infinite medium is. To quote, "The concept of semi-infinite medium can be easily understood as the maximum distance beyond which you are no longer able to hear your friend's voice if you are both found stranded in a forest or jungle." This is exactly similar to the concept of heat transfer, where if the point of reference is far away enough from the source where heat transfer effects are no longer sensed by the point of interest, we can define the distance as semi-infinite. To determine when you can use semi-infinite conduction modeling, you can calculate its Fourier number. Conceptually, this is the ratio of the heat conduction rate to the rate of thermal energy storage. At Fourier numbers less than 0.05, you may use the semi-infinite model.
Our idea was to make a lab for students to understand semi-infinite conduction by searing their own tofu slabs. We provided a 2-inch slab of tofu and asked students to sear it on low heat, taking it out periodically to take temperature measurements at different lengths along the tofu. Part of the lab asked to predict the temperature profile of the tofu and compare it with the data collected and discuss discrepancies with the semi-infinite model and the tofu. We tested the lab ourselves and found out we cannot take temperature measurements while the tofu was still in the pan because the residual heat from the pan affects the temperature probes. We decided on taking the tofu out on a plate and measuring its temperature and placing it back in the pan. We also chose to drain and salt the tofu to make it as dry as possible, preventing the water within the tofu from boiling and changing its temperature profile. We plotted the data alongside the semi-infinite model, which we'll discuss later.
Semi-infinite conduction calculations use a function called the error function, as shown here. The error function integrates the exponential form of zeta squared over 4, which can commonly be replaced by s. Zeta is equal to s over 2, and the more common form of the error function is written over here. In addition to the error function, there's a function called the complementary error function, which is shown here. It's equal to 1 minus the error function. Now you might be wondering what zeta is. This can be defined using a similarity transformation that assumes that temporal and spatial changes are relatively similar in this problem. This equates zeta over 2 to be equal to the position over 2 times the square root of alpha time. We get this value of 1.8214 from this assumption relating sigma, which is the length of the latent heat transfer in the 99th percentile, to x. This is basically saying that there's very, very little error in what x at its position is. So this is equal to 3.64 times the square root of alpha times time. And this means that the local temperature minus the equilibrium temperature is more than 99% of the initial temperature minus the equilibrium temperature for positions in the slab that are farther than the surface. With specified constant heat flux, we can differentiate the heat conduction equation shown here with respect to x and use the boundary conditions of the heat flux at time 0 being 0 and time greater than 0 being QW. Here you can see that we used Fourier's law to substitute for Q in this equation. This leads us to the derivation for the equations that we used in our calculations in the MATLAB code. It begins by stating that the difference between the constant heat flux, QW, and the local heat flux is equal to the error function with respect to the temporal and spatial changes. Then the temperature distribution is obtained by integrating Fourier's law, which gives us this second equation. We can then use the initial conditions of T initial being equal to T at x equals infinity, and the temperature at the local position that we're trying to find as equal to T at x equals 0 to find the third equation. This equation includes the integral of the complementary error function in order to account for the differences in the local heat flux to the constant heat flux that is included already in the equation. Here you can see a more common form includes zeta, but as we stated earlier, the similarity transformation allows us to substitute x for zeta.
This is the MATLAB model created to predict the temperature profile of the tofu. For the lab, students will have the chance to create their own model and approximate their inputs themselves. For us, we used the thermal conductivity of water as the thermal conductivity of tofu. We calculated the density using the weight and the volume. The specific heat was found through online resources, and the wattage of the stove was chosen to be 5,000 watts, which was on the higher end of the range of common wattages for electric stoves. Over here, we have the functions that calculate the overall temperature profile that Selby went over previously. We have zeta being integrated, with length of the tofu being iterated over from 0 to 2 inches of tofu. Here are the graphs that we generated. This is the graph of the predicted temperature profile over time of the tofu. The x-axis is the length within the tofu, and the y-axis is the temperature. Each individual line is a snapshot in time. As you can see, heat seems to be traveling within the tofu over time, with the temperature profile leveling out over time, which is what we expect. This is the same graph, but with the specific time snapshots we use in our experiment. This is a graph with the overlay of the data points. As you can see, the data seems to follow the same general trend of semi-infinite conduction over time. And here is an up-close shot of the same graph. As you can see, data is slightly off from the predicted values. This discrepancy can be due to a number of assumptions we made within the model, such as the tofu characteristics, the stove not heating the tofu evenly with a constant heat flux, and even if we kept the tofu at a low heat sear, water definitely could have escaped within the tofu, changing its temperature profile over time. For this lab, we also asked the students to account for the discrepancies within the model and the predicted values, and we think this is a valid learning opportunity for them.
As we demonstrated, students may not end up with a semi-infinite conduction model in MATLAB that exactly matches the temperature profile of the slab of tofu, which was the goal of the lab. This is still a valuable learning opportunity for students to create their own models and analyze the discrepancies between the semi-infinite model and their real-life data. We think this lab can be fun, tasty, and help students understand semi-infinite heat conduction modeling a little bit better.